Hello, my name is Reagan Brins, and welcome to Questioning Universe, starring our teacher, Mr. Larson.
Thank you. Thank you for having me.
We'll start off with our first question. Can fire have a shadow? Why or why not?
So I'm guessing that what you're asking is if you just have a flame, can that produce a shadow without any other object present? But the flame's emitting light. So in order to get a shadow, you have to have something obscuring that light. So, I mean, yes, you can get shadows out of flames. You just have to have another object in there to absorb or block some of that light from reaching some other part of the room. So yes, I would say flames can have shadows. Excellent question.
Thank you. All right, for our next question, I like, what would happen if I got close to the sun?
Well, you'd probably get a little hot, I'd say. The sun is, oh man, I want to say it's like 5,000 something Kelvin, which is pretty toasty. Yeah, you would burn up if you got close enough to the sun. If you're in space itself, though, and you're not just like in a spacesuit or something, before the sun burned you up, you'd probably die from, well, lack of oxygen is one thing, or radiation, not just the heat from the sun, but like bad radiation that can break your cells apart. So yeah, you would die.
Okay. All right. Thank you. For our next question, this is my favorite one. Why do boomerangs come back after you throw them?
I think that's a great question. Okay, so anything moving through the air experiences what we call air resistance. So like the air is made up of little particles. And so if you are, say, like in a car and you put your hand outside the window,
Yeah.
which I'm sure you've never done because
No,
you're safe when you're in your car, but you would feel the wind pushing back on your hand.
Yeah.
That's because it's made up of actual particles that have mass, so they can have momentum. They can push your hand. When you throw a boomerang, basically the way that you throw it and the way that the boomerang is carved is as it's spinning in the air, it makes a pressure differential on the bottom of the boomerang compared to the top. So what does that mean? You would have higher air pressure in parts on the bottom of the boomerang compared to the top of the boomerang. Now, if you have low pressure, so like low density air, and you have high pressure, high density air, basically what happens in physics is those air molecules want to move in a way that evens out the whole pressure for the entire system. So basically at the bottom of the boomerang, you have high pressure. That's pushing up on the boomerang because there's lower air pressure on top. So it would make it want to move through the air. As for like why when you throw it out does it come back, me talking about air pressure differentials is like a simplistic way of describing how anything can move due to air resistance. But basically the way that it's carved, it's going to push it so that it moves in kind of a arced path back towards you.
Sweet.
I think. I don't know. I'm just making all of this up.
That's right. Physics is a lie. Oh, I know what to do. I know.
Okay, so Mr. Larson, what would happen if me and you were in space and you threw me into a black hole? What would happen to me?
Well, if we were in space and I threw you in a black hole, first I'd be
elated. That'd be a great day for me because your life would be over.
I'm just joking, Emmanuel.
Thank you.
What would happen is this. So, like, basically, black holes have a really strong gravity field. And it gets to a point that we call the event horizon where you would need to be moving at the speed of light in order to escape this gravity. Nothing can move through space at or greater than the speed of light unless it's light itself or some other massless particle. So as you're going into the black hole, if you were like looking back at me as you're falling towards it, time dilates. What does that mean? That means the rate of time flows differently for you than it would for me. What you would start to see as you fell into the black hole, if you're looking outwards, like towards me, you would see everything speed up in the universe. You would also see light becoming what we call blue shifted. Basically, the wavelengths of the light would be decreasing as that light's going towards the black hole. So you'd see everything getting faster and faster and faster and bluer and bluer and bluer until the point that the light got so blue and energetic that your eyes couldn't even pick it up anymore. What I would see as you're falling in is the opposite. I would see time moving slower for you. I would see you slowing down. So if you were like waving your hand, it would start to slow and slow until basically you would come to a stop right before you cross this event horizon thing. And I would see light coming from you getting redder and redder. It would be red shifting. The wavelength of light would be elongating. So basically I would see you not just like disappear into the black hole, but like freeze on the surface of it. And eventually your light from you would get so red shifted that I would no longer be picking up with my eyes anymore. And so, yeah, it would appear that you disappeared.
Oh, that's okay.
Exciting, I know.
Okay, so my friend Carlos over there, he tells me that the Earth is flat. Is that true? Why or why not?
Well, first of all, Carlos is not your friend. He's trying to deceive you. The Earth is not flat. The Earth is spherical. It's not a perfect sphere. It's called an oblate spheroid. It's basically like if you had a sphere and like squished down the top and the sides around the equator would bulge out. This whole thing about the Earth being flat, even if you found someone who wasn't like university educated like thousands of years ago, they would tell you that the Earth was round. You could see it if you look at the horizon. You could see the curve if you like look out into the ocean. A boat traveling away from you, you'll see it start to go below the horizon. And those people can return to land. It's not like they fell off the edge of a cliff or something like that. So it's really easy to just see with your eyes if you look at a distance that the Earth is curved. The circumference of the Earth, this was something that was measured in like 200 something BCE, I want to say, by this guy named Eratosthenes. So it's long been known that the Earth is spherical, and even the size of the Earth has been known to within like 1% of its value for a couple thousand years. This whole business about like Columbus proving that the Earth wasn't flat, that's nonsense. That was made up and popularized by this guy named Washington Irving, who wrote a big hit of a book about Christopher Columbus. It's also the same guy that wrote Sleepy Hollow. Maybe you've heard of that story. Positing that Columbus was trying to prove that the Earth wasn't flat. That wasn't the case. We knew that the Earth was at least curved. Maybe some people didn't think it was a sphere. I think Columbus himself thought it was like a pear shape. But this whole Earth is flat thing is really a new phenomenon that basically I think people are trolling each other, trying to, just put an idea out there that's nonsense. And unfortunately, some people buy into it because they love conspiracy theories. Big NASA is trying to hide that the Earth is flat from us. I don't know why they would, but the Earth is not flat.
Okay.
Carlos is wrong.
So he's not my friend anymore. That's what I know.
Good, yeah.
Okay, that's all the questions we had today. Thank you, Mr. Larson, for joining us today.
Thank you, Emmanuel.
We'll have you on next time, I promise.
All right, sounds good. Thanks.